Welcome to the solutions to problem set number 7. This time a really nice and easy problem set. Exercise 1, calculating with congruences. I hope you noticed that part A was exactly the same as we did in the proof of proposition 8. Only in a different formulation. So we assume that A is congruent to B modulo n and C is congruent to D modulo n, and we are supposed to show that then also A plus C is congruent to B plus D mod n. But in our new notation, this simply means A residue class of A plus C is the same as the residue class of B plus D if the residue classes of A and B and C and D were the same to begin with. And this is exactly what we did in the proof of proposition 8 to show that the addition on the integers modulo n is well defined, except there I didn't call it A and B but K and K prime, not C and D but L and L prime, but otherwise it's exactly the same proof. So I'm not going to repeat that here. I hope you realized that, or that you could show it by yourself. If not, check the video with the proof of proposition 8. Okay, part B, the same, only for multiplication this time. So in residue class notation, we have to show that the residue class of A times C is the same as the residue class of B times D. This will become important later on when we define a multiplication on Z mod n. Z, then this shows that the multiplication is indeed well defined. Okay, now by assumption A and B are congruent, C and D are congruent mod n. This means exactly that B can be written as A plus some integer multiple of n, and D can be written as C plus some integer multiple of n, because then the difference B minus A is divisible by n and the difference D minus C is divisible by n. And so now we look at the product B times D and we simply have to expand this using the distributive law. So now we see here an n can be factored out. Okay, but now the expression here in the parentheses is clearly an integer because all those are integers. So I end up with BD equals AB plus some integer multiple of n, which means exactly that BD is congruent to AB mod n. And the special case C equals D follows immediately, because if they are equal, then of course they are congruent mod n, because the difference is 0. So that means I can, if I have a congruence, I can add the same number on both sides and the congruence is still true. And if I have a congruence and multiply it by a number, it's also still true. If the number is 0, then of course it becomes the trivial congruent. 0 is congruent to 0. That's why I excluded 0, but not for the reasons that this wasn't true also for 0, but simply because then it becomes a trivial congruence. Okay, part C is not true. You can't divide a congruence by any integer number, as this easy example here shows. For example, 1 times 2 is congruent to 3 times 2 mod 4. Why? Because this here is 6. 6 mod 4 is 2, so 2 is congruent to 6. But if I cancel the 2, then this is no longer true, because then I have 1 here and 3 here, and those are not congruent mod 4. So you cannot in general divide a congruence by a number. Okay, next exercise, the group table of Z modulo 6Z. This is of course trivial once you understood congruences or calculating with residue classes, but let's do it anyway, and we're going to need that for the last exercise on this problem set. So as always, first row and column are trivial because 0 bar is the neutral element. Now 1 plus 1 is 2, so here we have 2. 2 is 3, is 4, is 5 bar. We simply use adding representatives and then doing the bar over them. And now 5 plus 1 or 1 plus 5 is 6, so we have 6 bar, which is again the same as 0. Okay, and clearly this group will be commutative because adding integers is commutative, so we can do this without even thinking about it. So now the same with 2, 4, 5, 6 bar, which is 0 bar, and 7 is congruent to 1 mod 6. So we have this, and again this here. Now with 3, 3 plus 3 is 6, which is 6 bar is the same as 0 bar. Then we have 7, which is the same as 1 bar, and 8 bar, which is the same as 2 bar modulo 6. And here again 1 and 2. 4 plus 4 is 8. 8 is congruent to 2 mod 6. 4 plus 5 is 9, which is congruent to 3. So here we end up with 3 again. And finally 5 plus 5 is 10 bar, which is the same as 4 bar because 4 and 10 are congruent modulo 6. So this is the group table. So clearly commutative because of the symmetry to this diagonal, or because addition in the integers is commutative. Number 3, we have to finish the proof of proposition 8, which was that this here with this addition is an abelian group of order n. What we did in the video for lesson 7, we proved that this is actually a well-defined operation. It is also clearly an inner operation on this set because this again is an element of Zn, so I have closedness under this operation. And we simply have to check the group axioms. Now, if we're lazy, we say associativity is clear because adding in the integers is associative, but maybe we write down for once what we have to show. We would have to show that a plus b plus c is the same as if I move the parentheses. So whatever, let's do this. We have a plus b bar plus c by definition. Now here we have a plus b plus c. By definition, we take this number plus this number and then take the residue class. And now we have the parentheses here. And now, as I said, adding in the integers is associative, so we can write this as a plus b plus c, and then residue class. And now we do this backwards. This is by definition of our addition a plus b plus c backwards, and again by definition and this proves associativity. So if that is really clear for you, it's all right to write down this is trivial or this gets inherited from the integers because there we have associative addition. But if you're a complete beginner, please do this once or twice until it is really clear to you. Don't just say, well, yeah, it's obvious. The identity, of course, is the residue class of 0 because a plus 0, the residue classes is defined to be a plus 0, which of course is the residue class for a. So this is a right identity. Then we already proved that it follows that it's a left identity, or here you could say, well, the addition is obviously commutative, or you could just say it's trivial, it's obvious that 0 is the identity. Okay, Now the inverse, again, because we're in an additively written abelian group, which we just showed that, but in an additively written structure, for the inverse we do not write to the power of -1, but minus. So the inverse of the residue class of k is clearly the residue class of n minus k. Why? Because if I add those with this new addition, I get k plus n minus k. K cancels, so we are left with the residue class of n, which is the residue class of 0 in Z mod nz. So this is a right inverse, and by commutativity, which we will prove in a minute, also a left inverse, or by exercise xy, I don't know. So every element has an inverse. That obviously again lies in this set here. So we have proven that this here is actually a group. And commutativity follows easily from the commutativity in the integers, but let's write it down. This here is this by definition. Now in the integers, so you could write here commutativity in the integers, I can switch them around and then pull them apart, again by definition of this addition here. So this shows, and here I should also write for all elements of Cn. Okay, I'm being lazy. So this shows that the addition is commutative, so all taken together, this here is an abelian group with n elements, the n residue classes, so an abelian group of order n. And this concludes this proof. Now if you're a complete beginner and manage to write that down neatly, then that's already an achievement. So I won't belittle this proof here and say, well, it's all trivial. If you're really a beginner, this is not so easy to write down in an organized manner and to understand every step. So if you did that on your own, congratulations. All right, let's finish problem set number 7, which actually feels like taking a holiday this time. That's also important from time to time. So we talk about a geometric version of the Klein 4 group. We take R to be a rectangle, but not a square. Then I lose these two symmetry axes and only they remain, because if I reflect about this axis, this doesn't leave the rectangle invariant in the same position. So here the symmetry group consists of course of the identity, which does nothing. Then I have the rotation by 180 degrees. I lose the rotations by 90 and 270 because 90 degrees would not leave the rectangle invariant and 270 degrees neither. So only the rotation by 180 degrees. And I have the reflections about these remaining symmetry axes. Now to find the group table, let's do one composition together. If you're good at geometric thinking, which I am not, you can do this in your head. I wrote it down in permutation representation. This is easier for me. So I compose R with S1. This corresponds to, it's not the same obviously, but I use the permutation representation. So this corresponds to the composition of these permutations. This here is the permutation of S1. Why? Because 2 and 3 get interchanged and 1 and 4 switch places. And then the rotation by 180 degrees puts this here in position 3, this here in position 4, and so on. So this is the permutation representation for R. Now if I compose these, as we have learned before, composing permutations, I end up with this. Now what does this do? This switches 1 and 2 and 4 and 3. So this must be the reflection about axis 2. So this here corresponds to S2. So I have found out that R composed with S1, here R composed with S1 gives me S2. Then of course first row and column are trivial again. Now all these are clearly self-inverse. Why? Rotating twice by 180 degrees gives me the identity. I have rotated by 360 degrees. And as always, reflecting twice about any symmetry axis gives me the identity, because then I have done nothing. So here I get that all the elements are self-inverses. And then I simply fill out by using this technique here. And this is a bit surprising. This is commutative, because so far our symmetry groups have never been commutative, except for the trivial case n equals 2. So convince yourself that this group table is indeed correct. And now we can compare to the Klein 4 group, or we could say we have already classified groups of order 4. There are only two. There's the one where all the elements fulfill this condition, that composing with themselves gives me the identity or the neutral element. So this must be the Klein 4 group, but I think it's no mistake to completely write it down. The Klein 4 group was defined as follows. Here write E instead of 0, this, and this. And we already did the group table. Yeah, in the video for lesson 7, or one of the videos. So this is the group table. So you see, well, this is the same. If I call this here E, if I call this here A, B, and C. And this doesn't actually matter which one is which. You always end up with a similar group table. So this shows that these groups are indeed the same, only their elements have different names or labels. This is what we will later call an isomorphism. So to conclude, the symmetry group of the rectangle, which is not a square, is isomorphic. We will define that precisely later, to the Klein 4 group, which was defined to be the direct product of Z2 with itself. All right, and the last tedious exercise. You should have found out, if you did it, if you really did it, that this here is actually the same group as Z mod 6Z. So this direct product doesn't give me a new type of group of order 6 as did this one. This here is a new type of group of order 4, not Z mod 4Z, but this here not. Why? If you really write down the group table, there are 6 elements. Here we have 2 choices, 0 bar and 1 bar. Here we have 3 choices, makes altogether 2 times 3, 6 choices for these elements here. And if you're lucky enough, you have chosen the right order, which I by coincidence did, because of course I know what I wanted to have. And you do the group table. I was lazy here, I didn't do all the entries. Then you find out, well, this group table is exactly this one. Here last time I wrote 6 bar instead of 0 bar. Which of course is the same, but 0 bar is better. If you call these elements like that, then you end up with the same group table. So let's do one example. If I take this element and add it with this element, in the first component I end up with 1 bar plus 1 bar, which is 2 bar, which is the same as 0 bar, because here in the first entry we are in Z mod 2Z. In the second entry, I have 2 bar plus 1 bar, which is 3 bar, which again is 0 bar, but now in Z mod 3Z. So you have to distinguish the both components here. And this is actually the 0 element, the identity, which is the same as here. And also here in this row, if I, for example, take this plus this, the first entry I end up with 0 bar. In the second I end up with 2 bar, which is not 0 bar because we are here. And this corresponds to this here, and this is actually what we find here, and so on and so on. This, of course, has nothing to do with real group theory, because this is just a nuisance to write down, a tiresome exercise. Later we will see, when we talk about isomorphism and cyclic groups in particular, that because they have no common divisor, 2 and 3, this direct product must actually be isomorphic to this here. 6 is 2 times 3, and 2 and 3, their GCD is 1. But we will learn that in some weeks. All right, that's it for problem set number 7. I hope you enjoyed this week, that you didn't have to work as much and that the exercises weren't too hard. But still, as always, please write a comment. I'm very interested in how you are doing with this course. If you're enjoying the exercises, if it's too fast, too slow, whatever, please let me know. And I will see you in next week's lesson, I hope. Bye-bye.